We will start with integrating polynomials, and one of the important things at year 13 that we gotta remember is the two laws of indices, which are negative powers and fractional powers. So if you have 1 over x to the power n, it is x to the power negative n, and x to the power m over n. Oh, I'll actually if we have a root or a third form, x to the power m, nth root, it becomes fractional. So x to the power m is the power, n is the root. And so these are two of the laws of indices we have to keep in mind when we are doing or integrating polynomials. So let's do an example. So in notation is important. So integrate 4x to the power 7, let's say minus 3 over x to the power 5 plus square root of x dot dx. So we are integrating everything with respect to x, right? So step 1, before we integrate, we have to keep all the powers to either negative or fractional, because we cannot integrate a x to the power 5 at the bottom, nor can we integrate a third form. So this is still 4x to the power 7 minus 3x to the power negative 5 plus x to the power half dot dx. So we haven't integrated yet. Now integrate. So 4x to the power, increase it by 1, 8 divided by 8 minus 3x to the power minus 5 plus 1 is minus 4 over new power minus 4 plus x to the power half plus 1 is 3 over 2 over 3, and 2 goes up. We can put over 2 plus c. C is the constant of integration, and we leave the c. The final answer, simplify. It's important to simplify. Forward is half, so x to the power 8 over 2. So there's 2 minuses, becomes a plus. 3 over 4, I'll bring the x to the power 4 down. Plus, the 2 will go up, and you'll get 2 over 3 x square root to the power 3 plus c. And that's your final answer. Alright, moving on. Next we'll have a look at finding the constant of integration. So there is c. So the question would be, for example, if f dash of x is equal to 3x squared minus 4x minus 6, which is that's a function. You have to find the original function, so you have to integrate, and you're given a piece of information which you can use to actually find c, which is the curve f of x passes through the point 1, 5. So step 1 is integrate. Sorry, just give me a sec. Right. So step 1 is integrate. So we use the notation. So 3x squared minus 4x minus 6 dot dx. You can integrate this straight off, which will give you 3x to the power 3 over 3 minus 4x squared over 2 minus 6x plus c. Simplify, so 3 will cancel, 4 becomes 2, so you end up with x cubed minus 2x squared minus 6x plus c equals f of x. Right, so according to the information provided, f of 1 should be equal to 5, meaning so f of 1 should be 1 cubed is 1 minus 2 times 1 squared is 2 minus 6 plus c will be equal to 5, which is y. So if you go 1 minus 2 is minus 1 minus 6 is minus 7 plus c is 5, so c is equal to 5 plus 7, therefore c is equal to 12. So the function f of x then becomes x cubed minus 2x squared minus 6x plus 12, which is from here except now we know c, so there is a complete function. Okay, cool. Moving on. We're going to look at integrating exponential functions, which is y is equal to e to the power x. This is the only function whose derivative is the same as the original function, meaning if you differentiate this dy over dx of e to the power x, you'll end up with e to the power x. Or if you integrate e to the power x dot dx, you end up with e to the power x. Also, if you integrate e to the power kx, where k is a constant, dot dx, if you adjust, you end up with 1 over k e to the power kx plus c. So how does that work? Now if you look at it in reverse, just change color to make it stand out. So if I had, let's say, y, we're going to use differentiation to explain this. Y is equal to e to the power, let's say, bx, for example. So you go, okay, use the chain rule. You go y dash or divided over dx equals e to the power bx, and then you differentiate the bx, which will give you b, and you multiply with bx. And so e to the power bx, and that's your answer. So if I was to go in reverse, then it'll be 1 over b, and that's why that's 1 over k when you integrate. So if you integrate e to the power x, so let's do an example. Integrate, let's say, 5 e to the power 3x plus 1 dot dx. One of the things you can always do, if you have a number or a constant in front of a function, you can always take it out. So you end up with 5 integrate e to the power 3x plus 1 dot dx, or you can integrate the way it is. So if you integrate e to the power 3x plus 1, the answer will be e to the power 3x plus 1, and then you adjust that 3. If you differentiate, then if you are differentiating it with 3, if you integrate, it becomes 1/3, meaning 5 times 1/3 e to the power 3x plus 1 plus c. And that's how you integrate a exponential function. Integrating logs. So we are going to use natural logs, just like we have exponents e to the power x. So when we integrate ln of x, if you go back, if you remember when you differentiate, ln of x, that is y equals ln x. If you differentiate this, y dash equals 1 over x. So pretty much what we will integrate is, we are going to integrate rational functions, and when we would integrate rational functions, ln would most probably crop up. So if you have a function which is 1 over x dot dx, if you use the reverse of the derivative, you end up with ln of x plus c. Now keep in mind that I have put the x in absolute value, or the modulus of x. That is simply because it has to be positive, or else it won't work. So anytime you have a ln function after integration, has to be an absolute value sign. So absolute value sign is pretty much that, or the modulus sign. So cool. All right. So if you are integrating 1 over x, that's what you get. So let's try an example. Let's integrate 2 over 3x plus 1 dot dx. So you can just take out the 2 and then integrate the rest if you want. 1 over 3x plus 1 dot dx. I haven't integrated yet. I have just taken the constant out. You can, if you want to, you can just leave it there, which is fine. So this will give you 2 times ln of absolute value 3x plus 1 plus c, and then you adjust. So if you are differentiating 3x plus 1, you get 3, but since you integrate in here, you end up with 1/3 multiplied by 1/3, and you end up with that. And that is how you integrate a rational function to get logs, or the ln function. Okay, so we will still continue with the ln function, having a look at, if you have a derivative type function on the top divided by the original type function, for example f dash of x over f of x, So the rule is pretty much if you have f dash of x over f of x dot dx, you end up with ln of f of x plus c. So let's have a look at an example. So if you have, for example, if you have got x cubed plus 3, and on top you've got 3x squared, the top is the derivative of the bottom, dot dx, you will end up with ln of x cubed plus 3 plus c. Okay, let's do another. Let's say example 1. Let's do another example which is slightly different. So how about if we go 2x plus 2 over x plus 1 square dot dx. So if you have something like this, then well, I would expand the bottom just to see what I get. So we are not solving it yet, we're just expanding the bottom to see what we end up with. We end up with 2x plus 2 over x square plus, that's a perfect square, so I'm just going to skip a step, use the perfect square. So like it'll be x square plus x plus 1, so plus 2x plus 1 dot dx. So if you differentiate the bottom, you'll end up with 2x plus 2, and that's the whatever you get on top. Therefore the answer would now be ln of the function, which is x square plus 2x plus 1 plus c, and that is how you integrate a rational fraction whereby you've got the derivative on top, original function at the bottom. Cool, let's move on. All right, we'll have a look at rational. Now let's have a look at rational fractions or rational functions where of the sort of the form ax plus b over cx plus d, and d could be 0 or b could be 0. So if you have a top heavy function where bottom you only have one term and the top you have got multiple terms, you can spread them out and see if you can simplify them before you integrate, using the rule of if you have something like a plus b over c, you can separate them into a over c plus b over c, and if you can simplify that, then you integration becomes much easier. So let's do that here. So if you integrate this, you'll end up with 2x over 2x plus 1 over 2x dot dx. That simplifies to 1. So you integrate 1 plus 1 over 2x dot dx. So this one would simply be x. So if you integrate 1, you get x. If you integrate 1 over 2x, now if you remember 1 over x, if you integrate, you get ln of x. So if you integrate 1 over 2x, well, you adjust, you will end up with, so you can just take the half out, and that's a constant, and then it simply becomes well, from here it can just become 1 integral 1. Sorry, I'll just so this can be half times 1 over x, and that can come out of the integration sign, so plus half ln of x plus c, and that's your function right there. So this is just if you split that up. Okay, moving on to more. Alright, so if you have something like 4x plus 5 over 2x minus 1 dot dx, for something like this you can see there's 2 terms on top, 2 terms at the bottom, and therefore you cannot sort of separate them. Easiest thing here to do would be long division, which we learned in factor theorem, remainder theorem. So for in this one we will be using long division with a remainder. Therefore we put the top in the divisor and let's divide. So what multiplied by 2x will give you 4x? 2 times 2x is 4x. 2 times minus 1 is minus 2, and then you minus. So you end up with the 4x minus 4 is 0. 5 minus minus 2 would be 7. Therefore, that function becomes the quotient, which is 2, plus the remainder, which is 7 over 2x minus 1. What this means is, I'll just use a different color, simply that 4x plus 5 over 2x minus 1 is equal to 2 plus 7 over 2x minus 1. Therefore, now you can rearrange this function as another integral of 2 plus 7 over 2x minus 1 dot dx. And now you can integrate. So 2 would be simply 2x plus, and then 7 can come out and you can adjust with the 2. So 7 ln of 2x minus 1 plus c, and then you differentiate, you get 2, and adjust, you get 2 at the bottom. And that's your solution right there. Alright, let's have a look at integrating trigonometric functions. So let's have a look at identities first. So if you have y is equal to sine x, y dash would be equal to cos x. This is just from the list of identities you get on the formula sheet. And if you have got y is equal to cos x, then y dash equals sine x, negative sine x. Then if your y equals 10x, y dash equals sec squared x. So you can use 10x is equal to sine over cos, and then use quotient rule, and you end up with, after simplifying, you end up with sec squared x. Right. Okay, let's have a look at a simple one. So for example, if I just take that out, so if you go y equals sine 3x, for example, and if we were differentiating, we'll end up with y dash equals sine 3x, and then you differentiate the 3x, you get 3, and you put it in front. Therefore, if you were integrating, oh sorry, I mucked up, my bad. If you differentiate sine, you don't get sine, you get cos. So you differentiate sine first, you get cos, and you retain the 3x. You can put them in brackets if you want, which is fine. Then you differentiate the inside and it comes out. Now if you are integrating this, for example, if you're integrating cos 3x dot dx, then what you do is you integrate cos first, you end up with sine, so which is fine. 3x comes here, and then you adjust. So you differentiate 3, and then instead of multiplying with 3, you divide with 3. So the 3 comes in front, becomes 1/3 plus c, and that's your solution for basic integration of a sine or trigonometric function. Okay, so using these scenarios, there's rules for sine, cos, and sec squared going in the opposite direction. So for example, if you so if you have an integral of sine ax plus b, for example, sine ax plus b dot dx, you will end up with a negative 1 over a, that's the adjustment, cos of ax plus b plus c. And if you have cos of ax plus b dot dx, you end up with 1 over a sine ax plus b plus c. And if you have sec squared, we are going from there, kind of there, to that side. And so if you have sec squared ax plus b dot dx, you end up with 1 over a 10 of ax plus b plus c. And so any particular scenario which has got a and b as constants, for example, if you get sine of 2x plus 3 dot dx, you end up with negative 1 over 2 cos 2x plus 3 plus c. And that works for any generalized situation which you are integrating sine, cos, or sec squared. And for any other functions like cosec or sec or cot, then there are actually identities for those as well. Right, moving on. Let's do some different types of trigonometric, basic trigonometric integration. So we just use the whatever we just learned before. So if you have let's say for example 2 sine um, 2 sine of 4x dx, so firstly you can just leave the 2 as it is, and sine will become so 2 would be 2 out, and sine becomes cos 4x stays plus c, then you differentiate the 4x, you get 4, you adjust it, you divide it by 4, and cos, sine to cos is a negative, so it'll be a negative 2 over 4, which you can simplify to negative half cos 4x plus c, and there you go. Second one says cos half x plus pi is a constant dot dx, so just like ax plus b, and if you integrate cos you end up with sine, so write sine, the bracket doesn't change, half x plus pi, and then if you differentiate half x you end up with half, and so if you adjust half, 1 divided by half would give you 2, and you put 2 on the top plus c, and that's how you adjust. The last one is I sec squared bx dot dx. So sec squared, if you integrate you get, or if you differentiate 10 you get sec squared x, therefore if you integrate sec squared you get 10, and therefore you leave the a there, you get 10 bx stays plus c, you differentiate bx and you put it at the adjusted below a, and you get a over b, and that's how you integrate basic trigonometric functions. Alright, we are going to use some trigonometric identities while we integrate. So this is just to, so the whole idea is if you have like a, sometimes if you have a scenario where you have like a sine and a cos and they're multiplied and you want to integrate, it'll be easier if you just have all of them in sine or all of them in cos. Or if you have a power, for example, if you have 1 minus sine squared x, and if you end up with like a cos 2x, it's much easier to integrate. So, and that's why we use integration. So whenever you have a function which is looks weird and has got a whole lot of trigonometry in there, the first go-to point would be your formula sheet of double angles, and then you can use products and some identities. There's heaps of identities which I went over yesterday, but sorry, I went over today. But let's do some questions. So example, let's say we have to integrate sine 2x cos 2x dot dx. Right, so you've got a sine a cos a scenario, because as you can see 2x is common in both, so this is you can use a double angle. Okay, so I'll just use a different color just to show. So the double angle identity says that sine of 2a equals 2 sine a cos a. So if you have sine a cos a, you end up with sine 2a. So that would mean that if I use the double angle formula here, I'll end up with sine of wait, hang on, just give me a sec, sine 2 sine cos a. So there's a 2 here which we have to adjust. So if we take the 2 to the other side, it becomes half sine 2a is equal to sine a cos a. Because you've got a sine a cos a, there's no 2 there. So we can substitute and end up with a half sine 2a dot d. Sorry, my bad. Not 2a, but 2a would be 2 times 2x, which would be 4 sine of 4x dot dx. So just to recap what I've done so far, I have used the double angle formula. I've adjusted it because in the double angle it's 2 sine a cos a is sine 2a, whereas what we have is sine a cos a, where a in this situation is 2x, and therefore I take the 2 away and I put it on the other side, becomes half, so the half is there, sine 4x dot dx. Now we integrate, so we can take the half out actually. So we've got half, so if you integrate sine, you get negative cos, so you might as well put it there, so you get cos of 4x. See, I left a little bit of space between half and cos because I'm going to adjust. If I differentiate 4x, I get 4, so I multiply this with a quarter, and that equals to negative 1 over 8 cos of 4x plus c. So I have used a trigonometric identity, which is the double angle formula. These double angle formulae is on page 3 of your formula sheet. There's a whole bunch of them. Cool. All right, let's do some more. All right, so let's integrate cos squared x. So cos squared x, there's a double angle formula again, which is cos 2a equals 2 cos squared a minus 1. So if we rearrange it to make cos squared a the subject, let's see what we get. So we end up with 2 cos squared a equals cos 2a plus 1. I'm moving the 1 and then divided by 2 or multiply by half on both sides. I end up with cos squared a equals a half cos 2a plus 1, and I can put all that in a bracket if I want to, just to make it correct. So now I can substitute in on the left hand side and using a different color hopefully. So I end up with a half. I can keep the half, it's a constant outside, therefore I don't have to use brackets then, and I can get cos 2a plus 1 dot dx. Well, I can use brackets if you want to. This is, oh sorry, my bad, not a but x, so a is x in this instance. So now I can actually integrate without sorry, just give me a sec. Yeah, let's so I have half outside, cos becomes sine 2x. If you differentiate 2x, you get half, or well, you get 2 half on the outside, plus x, and then plus c, and then I can take the half inside and multiply, end up with the 1/4 sine 2x plus half x, or x over 2 plus c. And that is how you integrate, again using a trigonometric identity using the double angle. Let's do some more. All right, let's go and do something, venture into something a little bit more complex. So the question looks something like 2 cos 2x sine x dot dx. Now one of the things you will notice is cos has a 2x and sine has a x. So multiplication of cos and sine usually comes up in a product rule, and one of the product rules with a cos and sine specifically is 2 cos a sine b is equal to sine of a plus b minus sine of a minus b. Sorry, I ran out of space, so I've written it this way. So a from the left hand side is 2x and b is x, as you can see. That comes from here and here, a cos a and sine b. So if we use the rule and simplify, we end up with sine of a plus b would be 2x plus x, which is 3x, minus sine of 2x minus x, which is x. Therefore, so you can clearly see 2 cos a sine b, 2 cos a sine b. So we can just directly substitute this into our integral sign and see if we can integrate. So we get sine 3x minus sine x dot dx. So sine becomes cos, or negative cos. So negative cos 3x, and then differentiate, you get 3, and then you adjust, you get 1/3, and then minus, and then another minus, sine becomes cos, so this becomes plus, and you get cos of x plus c, and that's your answer. Okay, so I will leave you do some more problem solving and get back to me, but I have covered a whole bunch of different types of integration, including trig, and watch this space for more videos. Thanks for listening.